Okay, so I started like a Zoom meeting now. Now I'm like recording to the cloud. Make sure I think. You want? I think I need to share patient your screen. You are sharing screen. Your screen sharing. Let me tell you also like one thing I also want to bring your attention to. Like, please pay attention with me. Please pay attention. One thing like I also want to bring your attention to. If you go to assignments, so like if you go to assignments here, okay. If you go to let me bring your attention to this point. If you go to like project like groundwater supply, project number 2, okay, you will find that whatever I'm doing this class, I already recorded for you on YouTube. So like you can go to this YouTube video. And like this YouTube video, it also has something like if any steps you are like getting stuck in any of these steps. I don't know why YouTube is okay. If you're getting stuck in any of these steps, you can find like the content of this video. So like, for example, if you are stuck in PEST program location, for example, then if you click here, you'll just go directly to this. So basically you have 2 recordings for this lecture. This recordings that I'm doing right now, and like this recording, which you will also find here. Like if you go to like the groundwater project description, you'll find this recording here. Okay, so you have 2 recordings for like for this what we are doing. Okay, so let's get back to what we are doing. So let's get back here. This is like the model setup. So we have something like this. Okay. We have so let's before we start like our model, let's just review what we did so far. So we are now like your project has 3 components. It has a model setup, which we will finish today. It has like a model calibration, which we will do today, and then the model application we will do next. For the model setup, before you set up a model, you need to define like the model purpose. Because like depending on the model purpose, everything will be different. So here, like for example, the model purpose is groundwater supply design. If this was like a contamination, like if that was like to simulate some contaminant and like some remediation, then that would be like a different model purpose. This equation would be like you would still have the flow equation, but you need another equation for transport, for example. If so, depending on the model purpose, you need to start by like defining the model purpose. And then once you have the model purpose, then you put like your governing equation, like your mathematical model. So we have like this simple mathematical model for our 2D aquifer, which basically has like the hydraulic conductivity, and it has this boundary condition. And once this model is simulating, it's the groundwater head. So basically, this model will solve for the groundwater head, giving the definition of hydraulic conductivity and boundary conditions that you define, or like general force and things that you have. For our boundary condition, we have like different types of boundary. So for example, like here, we have like a groundwater divide. So this is like a no-flow boundary. At the base of our aquifer here, this is like another like no-flow boundary, for example. On the top of our aquifer, like the aquifer top here, we have like recharge, like here all the way. This is here. This is like your this is your groundwater table. So this is like your groundwater table. Like this is the land surface here, and you have like recharge here, like getting the more recharge, like you have recharge here. Other boundary we defined as a river. So we have like a river here, and this river like recharge. That's like a source term. It adds water to my system. The river it would take water from my system. So here, like the head of the river is 100. If the head in your aquifer here is higher than here, then water basically will flow from your aquifer to the river. If the head in your river is higher than your aquifer, then water will flow from your river, from the river to the aquifer. So basically, we have like this called like head dependent flux. So depending on the head, you will determine like the magnitude and the direction of your flux. And then we have like a pumping well. So the pumping well actually like so you have a pumping well here. Doesn't look so nice. Anyway, so the pumping well, like the whole idea of this design is that we want to design this pumping well and to see how much water we can pump out without causing a certain like drawdown. So we will add the pumping well, but our pumping will be like zero. Okay, we'll just add it to the model, but we will make like we are not like because initially like this is like the pre-development, we have like pumping is equal to zero, we are not pumping anything. And recharge that was given, I think, as 0.000 like 8 meter like per day, for example. Here, this is pumping is like meter cube per day. So here we are giving like 0 meter cube per day. This will depend on that. Okay, so we define like our boundary condition. So this is like we create like a conceptual model. In the conceptual model, we will like add all this part of our conceptual model. And our conceptual model, we also define K. So here we define like different values for K, different zones. Like we created like these 6 zones. And we assign a value. Each one will have like a different conceptual model with respect to the K because each one is differently. But with respect to this boundary, I think we all will have the same. Okay. Another part of our conceptual model is the head observation, like the head that we are observing in the field. We don't need this to run the model. Like the model will simulate the head. So, like once I run this model, it will give me the head. Will simulate this head. This will be the head simulated. And I will compare it with the head that I'm observing in the field. So I need to add this one, not for running the model, but once I run the model, I can compare it what I'm observing in the field, and then I can adjust like a model accordingly. So I think last time we stopped here, we defined like this A, we added like this boundary condition, recharge, river. Like I think we stopped here, like adding the pumping well. So let's just add this pumping well, and then we also add like bed observation. Let's like do these 2 steps, and then we will see about like how to create a numerical model afterward, how to convert our like conceptual model to like a numerical model. So basically, the problem is telling you. Like if you have like what I gave you, like this sheet that I gave you last class, you have like this sheet that I gave you. Like if you go like now we are at step at the river at the pumping well, we are at the step 1.8. So if you go to like second page in 1.8, it's telling you like the problem or your project is telling you that there is a pumping well that will be like installed, and this pumping well is half the way between like B10 here. So here, these are my observation point. So here, for example, like I have like B1 here, for example. This is my observation point B1. I have this is like B3, for example. I mean, whatever. I mean, this is like B3, for example. Like I have my observation point B3. This is B10, for example, is somewhere here. Okay. This is B10. I have there are like 12 of them. Like B12, for example, will be here. Okay, like B12, and like the river is like I have my river here. Okay. So I'm telling you, like the problem, like if you read your project description, it's telling you add a pumping well, like that's half a distance between like this guy and this guy. So it should be somewhere. Half a distance between this guy and this guy, we need to put like pumping. Okay. So this is our, again here, this is our observation well. So here, for example, at B1, this is the X, look like the X coordinate. Oops. This is B1, for example. You see here, B1, that's like the X coordinate of B1, that's like 450, and that's like the Y coordinate 1.25 kilometer, for example, for B1. Okay. And like at B1, the heads that I measured here at B1 is 107.98, like 108. That's like the heads that I measured here. Okay. The heads that I measured at B3, for example, is 107.4. Okay. And if I put all these values, I could interpolate them and I could get a figure that looks like this. I could create, like if I, like I have these, at each of these points, I have the head value. If I interpolated this head value, I will get a contour line like showing you the head that is like this. Okay, this is what I observed in the field. So my model will simulate the same. But now we want to add a pumping well that is somewhere here. Okay, that's what we want to do now. And if I calculated this distance, like from here to here, like if I calculated, so for example, like B10, the y coordinate of B10, that's like 950, for example. So like with a pumping well, like the coordinate of this pumping well that I want to add, I need to find like the x coordinate, like the x coordinate here and the y coordinate. The y coordinate will be the same as B10, so that's like 950. Okay. And the x coordinate you can calculate it because you know the coordinate of your river and you know the coordinate of this guy, so you can calculate the x coordinate. Like I calculated it as 3955. Okay, so that would be the location of your pumping well. It's this x and y coordinate. Okay, so let's add it. So like to add this one, let's just add this one. Like so, to add this one, we need to open our project. So like please open the project that you did last time. So the way I do this, I come here to apps anywhere. If you have the program in your computer, that's better than like this one on apps anywhere. Like, but I don't have it because I cannot like. So like you go to apps anywhere. Okay. You go to apps anywhere. And then you can write like model muse, for example, like model. Or if it's better to have it in your computer, actually, model muse, okay? Then like you launch this one. So you open the app, you get to click OK here. So you launch this one. And and then it should launch, like takes time. But if you already have it on your computer, you can just open it and like open whatever project you did last time. But on apps anywhere, it just takes time, so we have to wait. Let me click it again. Let me launch it again. So if I launch it again, yeah, it's still like taking time. See, that's why it's always a good idea to have this installed on your computer instead of using these apps anyway. Because okay, so finally it's after waiting and waiting and waiting. Now here, okay, now like now so now let's start here. So like here, what should I select from here? Open an existing model muse project because we already have one saved from last time. So I click like open an existing model muse project, then I click next, and then you see where you saved it. So like for example, here I saved it here. If you go to lessons, this is where I saved it. I don't like it. That would be different for each one of you. And then like projects, for example, like section 2 model setup. So this is the name I give it, like model setup for group 2, your group 2. And then I click open. And then if you click open, then takes another year to open it. Okay, so now here, this is the project that we have from last time. This is what we did last time. we have from last time. So we can confirm that we are opening the right project, for example, and we have like the right thing. So hide floating line. So to do this, you can visualize your hydraulic conductivity field, for example. So you can come here, you can come to data set, required, hydrology, KX, apply, and close. Then that's what we defined last time. So here, for example, this is 8, this is 21, this is 300, this is 650, this is 150, and here I have like my river somewhere here. Okay. So basically, that's like we can remove this visualization. So to remove the visualization, you can come here, you can add none, apply, and close. So what we want to do, we did all this last time. Like we did the restart, we did the river. What we want to do is like we want to add a pumping well. So like to add a pumping well, to do this, that's you do it from here. Okay, so like remember like last time we created, for example, or before we do pumping well, let me just let me show the image first. So like if you go to here, edit image, and then like make the image visible, so I make this image visible. This is like my river is here, this is B10 is here, and I want to add a pumping well somewhere here. Okay, so I come to this is create a point object, because this is a point object, and then I want it to be like middle way between the river and the B10. So I can just put it anywhere here now, doesn't matter. And then I could give it a name. So the name is pumping well. That's like the names that oops, what's happened? That's like the names that I give it. Then I go to MODFLOW feature. This is my well package. So I select this well package, and then the starting time is -1. The ending time is 0. Now here, the pumping rate interpretation direct. I want to add like this number directly. So if you select this direct, then you will have here pumping rate. And again, in the pre-development case, the pumping rate is 0. We are still not pumping anything. We are just setting the pumping well, but we are not pumping anything. So it basically it will have no effect on you. It will be just there, but it will have no effect. Okay, because we are not pumping anything in, when we are setting up this model. Okay. So we click OK. Oh, before we click OK, we go to vertices. So we go to vertices and we enter our correct vertices, because this is not the accurate location. Like the accurate location is this one. Okay, so we just enter like the accurate location. So go to vertices, and that would be 3955, and that would be 950. So that will be the accurate location that will place this dot exactly between your B10 and your river. So if you click OK, then you see now this dot moved a little bit here. And you see like if you click on this dot, you see like you're getting the exact like this is now between this one and this one. So now we added the pumping well. I can after I added it, I could go to this like red arrow here, select object. I could create on it, and then here, for example, if you go to comments, I could make visible. So if I click visible here, then it will show me the name of this thing, pumping well. Let me delete the image, like, or unhide the image. So edit image, you select here, then you click OK. So you see now I have this pumping well. Maybe I click on it again. Maybe this font is small, so I could come here. I could change the font, for example, to, let's say, like 20. I don't know, like 24, for example. Then I click OK. Now you see this is too big and maybe it's not the right location. I could come here, for example, like make an offset of 40, for example. And then if I click OK, then it will like offset this here. Okay. And I could come back and I could maybe change the font back, make it, I mean, this too annoying. This big font was annoying. I could just select 12 or 14, maybe, or 12. Okay. So you can have any, okay. The offset, okay, let me change the offset again. 20. Okay. I could also, another thing, I could add a comment. Like if I want to show more than this, what is showing here what's like printing on the screen is the pumping well name, but you can add a comment. Like I could replace this, for example, with like pumping well, and then I put like something like pumping well. I could do something like this. If I clicked OK, then you see here I have like pumping well and pumping well. Okay, so you whatever command you add, it could show also. But if you don't want to show anything, you just want to show the well name, then you remove this one. You come here and then you click OK, then you only get the pumping well name. Okay, so now we added the pumping well. The remaining part is to add like this head observation, like the head that we are observing in the field, so that when we run our model, we can compare it with what we are observing in the field, and then we can decide what to do with our model accordingly. So to add the head observation, to do this, like that would be like in your documents that I gave you, point 1.9. So you go to File, and you go to Import. So like this, how you do it? You go to File, you go to Import, and then you go to Import Points. And here, like at the import point, like you select this one, select like specify layer instead of elevation, because this is how I prepared this data, by like layer number, not by elevation, and set value of the intersected cell. Okay, you just select like these two here. You can give this like a name, like for example, like head observation, for example, like this is the names that I would like to give it. Head observation, and then like the feature. What is this? This is head observation. So basically, you select this one. So here, you do these two selections, specify layer instead of elevation, set value to intersect cell. So make sure that these two are selected. That's how I like this, how I prepare this data, how I want to import it. And then like here, head observation package, make sure in feature you select head observation package. Okay. So if you all at this step, the remaining part would be just to import the data. So like here, you import it from the files that I asked you to download. So basically, like you open the file and see where, like, so for example, like in my computer, I'm saving this here, for example, like project file. Like you see this where I'm saving this data, but where I'm saving this data is not showing me the file, like that .csv file. Why is it not showing me this file? Because here the file type that I'm specifying is text file, while like my actual file is CSV file, like comma separated value file. Okay, so you select this one, and if you select this one, you will see the file appearing. If you have your data saved as like text file, you can import it as text file, but like here I have it as comma separated file. Okay, so basically you should like find like this file that I asked you to do, like to download, and then if you click open, and now you find all these value are here. You could also enter them manually by hand, one by one, but like here, it's easier to just import them from a file than entering them manually one by one. So if you want to enter them manually, you can do this. Basically, this is the X coordinate of my observation. Like here, for example, this is my first observation point here. Let me show you. Like this is like, for example, my first observation point, like B1 here. This is like the X coordinates, the Y coordinates, the head, like how much head I'm measuring in the field. So basically, that's what you see here. Okay. So you see here, this is the observation name. This is the X coordinate of this point. This is the Y coordinate. This is the head that I'm observing in the field. And these are just some statistics flags that we will use on when we do like for model calibration. Okay. So this is already, I defined these ones for you. Okay. And the time is like 0. So this is at the end of our simulation. Yeah. No, if you are saving it as a text file. Okay. So basically, yes. So like I think like the mistake he did, like when he didn't select like comma separated file, he selected all files. That's why he got this error. So, but like you just do like if you just select comma separated file, and then you will get something that looks like this. Okay, so you should all have something like look like this. If you click OK, then you will find here. This is points like my 12 observation points, like B1, B3, B4, like still like all of them. I have them imported. I can confirm this. Like I could like come here, select this one, for example, double click on it. So this is B1. The vertices of P1 is X is equal 450. The Y is equal 1.25 like kilometer, for example. And, and here, this is the heads that I'm observing here is this time, is this much at like this time, and this is this. Okay. And if I want to visualize it, then again, you come here, you do make it visible, and then you click OK, then here is B1, and I can change the font. If I want to make many of them visible at the same time, this is also possible. Like the way to do this, you can select like one of them, for example. I'm not going to do it for all of them, but I will just show you how. And then you hit the Shift key, and then you click, you select all of them. Let me just select 4 or 5 of them. Okay. And then you click on any of them. And then here now I have like 1, 2, 3, 4 of them selected. And then I could make them all like, for example, visible. Okay. Then you see here, this is B3, this is B2, this is B4, this is B5, this is B6, and so on. Like this, for example, should be B10. Like if I made this one visible, for example, that should be like B10. Okay. So if that's like if you would like to do something like that. Okay, so let's see what we did so far. So I think so far we are almost done. Like we are almost done. Like we set up our like conceptual model. We define the hydraulic conductivity. We define recharge. We define this pumping rate. We define the river. We added like the head observation that you will use for comparison purpose. I think like now the next step is like to convert this conceptual model that I created here to like a numerical model, and that MODFLOW. So MODFLOW, what MODFLOW will do, MODFLOW, that's like the solver that you will use. What MODFLOW will do, or before what MODFLOW will do, what Model Muse will do for you is that Model Muse, whatever you converted here, it can convert it to a numerical model, which MODFLOW can use to solve like this equation. So basically, that's what like you don't have to convert like this conceptual model to a numerical model. Numerical model is that like you convert it to a grid cell, and basically what MODFLOW will do, it will estimate the head at each of these nodes. Like it will estimate it here for each cell, it will estimate it here, 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 it will estimate it here. So basically at each of these nodes, MODFLOW will solve this equation and estimate the head at each of these points. So, and for example, if I want to compare, like if I want to know the head here, for example, at this point, like B3 is here, I can just interpolate between these 4 points, and it will give me the head of B3 for comparison purposes. Okay. So now let's just make few checks, and so like now we are in step 10.1.10. So let's go to model. Now, like step 10.10, like we will do a few checks, like few settings for our model before we start creating the numerical model and running it. So like we come here, like model. I think I told you go to layers and group. So here, like in layers and group, we want to define like what type of aquifer is this? Like, is this like a confined? Like you see here, MODFLOW can only, like you see here, like I told you, there are 2 types of aquifer, confined and unconfined aquifer. What MODFLOW will do, it can solve it. Like let's get back. When I wrote this equation here, when I wrote this, like you see, this equation here, is this for confined or unconfined aquifer? Confined, right? Yes. No one told me you're writing the wrong equation. This equation is for the confined aquifer, and this is an unconfined aquifer, right? This is an unconfined aquifer, right? Because we don't have a confinement there, right? Yes or no? Is this confined or unconfined? Unconfined. And is this equation for a confined or unconfined aquifer? For confined, right? Because for an unconfined aquifer, there should be like an H somewhere here, because like the H is variable, right? So there should be an H here and H here, right? And none of you told me, oh, you are writing the wrong equation. None of you corrected it. That's all of you, all the class. But that's okay. You know, the reason that I wrote this equation, because that's exactly what MODFLOW do. MODFLOW will solve this. Like if you selected here, MODFLOW will not solve for unconfined aquifer, because that's very difficult. What MODFLOW will do, if you selected the convertible one, what MODFLOW will do, it will solve this equation for the unconfined aquifer. Okay. And then after it solves this equation, it will calculate like the head at each node. And if it found like the water level is different than the head, then it will know that this is an unconfined aquifer, and it will accordingly adjust the head and adjust the storage coefficient. That's how much works. Because it's difficult, like that problem also, if H is variable, it's also difficult not only to solve it analytically, it's also difficult to solve it empirically. So that's how MODFLOW will solve this equation, and then if the water level, like if the head and like the water level are different, it will adjust the head and the storage coefficient. And then, so basically here you can select two options. You can select either like confined aquifer, if you know that this is a confined, or you can select convertible, and then it will like, if this is an unconfined aquifer, MODFLOW will convert it. Okay. So like, so you do this one, you click OK, then you go to model. I think the second one I have on my list here is like a model time. You can check the model time. So the model time, again, this is like I'm starting from this and ending here. This is all okay. This is a steady state. Here is a day. So that's all fine. So I don't need to do anything here. I just click OK. So that's the model time. And then go to model again. Model options, like here's this one. And then model options, go to options, select this one. Like I just want you to select this one, continue running even if the solver closure criteria are not met. And this would be important for model calibration, because when we are calibrating the model, sometimes the model will not converge, and we don't want the calibration to get interrupted if the model didn't converge. So just click on this one here for like the options. Program location. Okay, now this is the important part. Like come here to model, and this is the program location. Okay, so here, like this is what I told you that you need to do at home, like to install. Again, I told you like I'm not gonna spend like waste like half an hour in this class, like installing like MODFLOW. So this is what I already provided you with the link. So you have like you go to like, I sent like a class announcement with a link to Google Doc where you have the installation step and the video also. So if you have MODFLOW installed, then it should be something like 10. So for example, like here I have MODFLOW installed, and basically to install it, you just like you will download it as a zip file, you unzip it, and you just put it wherever you put it. So here I have this where I have MODFLOW. This is where I have the executable, and I will select this executable like MODFLOW 2005. So basically make sure that the BEST know where this program is, because remember, like BEST, this is like not BEST, like Model Muse. Like Model Muse, this is just a graphical user interface for so many programs. Like for all these guys, it's just a graphical user interface for all these guys, and even more. Like this is just the MODFLOW family, guys. There is even like Sutra and FAST and other things. And this is just a graphical user interface. It's just like, so make sure that it knows where you put your executable. So here, if you don't have your BEST know where your MODFLOW executable is, it's not going to work. Okay, so you click OK. And then like after we do this, like after we make sure that we selected where this file is. And like here, I put you the link to install this. I'm adding the link, the YouTube video link. You should have installed this like a couple of weeks ago. Model, go to like manage parameters. So here, like just double check. So this is our parameter values that we defined last time. So K1 is 8, for example, K6 is 150. So I think we are done. Like we are done with the model setup. Like the next step is just like to convert this guy to this guy, like the numerical model. And MODFLOW will do this for you. MODFLOW will take your conceptual model, it will convert it to numerical model, write all the input file for MODFLOW, run MODFLOW for you, and MODFLOW will generate the output file. So how to do this? That's very simple. You just run the models. That's all you need to do. You don't need to do this yourself. So basically, how to run the model? You come here, like you see this guy here, run MODFLOW. So if you clicked on run MODFLOW, it will tell you save it as a name file. So this is, let me write this down for you, like your model name, like name file. Like this name file will contain all the file names for all your input and outputs. And I think like the outputs, like not all the output, but the output, the main output of MODFLOW, it will be contained like in this file. And again, you're not going to do this by yourself. Model Muse will do this for you. Okay, so you click save. Okay, and then Model Muse is creating the model, is running it, and here I got like a warning. I'm not running. Let's see what's happening here. So if you did this, like I don't know why is it. Let me close this and try to run it again. Sometimes it's like slow like this, but that's okay. Okay, let me do this again. So let me close this one. Let me do this again. Like come here, like see this is run MODFLOW. You click run, you select this one, select save. You do this one, you run it. Now it's running. Okay, so now it's running. Like after you run it, you will get like a screen that looks something like this. This is like your one-time step. If you close this one, okay, now let me close this one. If you close this one, then you will get a file that looks like this. This is like, again, this file will have like your model name, whatever that model name is, .list, LSE. That's like your list file. And your list file, that will have your main input and output like of your model. So like if you look at this list file, for example, here, this is your grid. It's like 50, like, and by 10, for example. This is like your river, like how you, like this is your model top, your model bottom, for example. So these are this is how your hydraulic conductivity, like K1, how you define like your K1 value. This is like how you define like K2 value. This is how you define K5 value, K6 value. Again, Model Muse will do this for you. That's why you use this graphical user interface, because it will do this for you. Remember, I told you when I did this before, I didn't use a graphical user interface. So how to create this file? I just used to create using a programming language. So you can use like MATLAB, for example, or you could use Python, and then you can create like your input like just with a programming language. But here, Model Muse will do this for you. Okay. This is like your K parameters that you define, like 8 here, 20, whatever. So this is the K parameters that you define. Again, this is your hydraulic conductivity field here. That's how it would look like. But anyway, I can just skip all this. You can look at these cells one by one, or like all these things. Okay, I got like here, like you see here, I got like an error. Why I got an error? Because I forgot to do one thing. I forgot to define my initial condition. Usually for steady state, you don't need an initial condition, but it's usually a good idea to have an initial condition for your solver to converge. Like initial condition is the initial head state. So how to define the initial condition? You go to data, you like edit data sets, required, hydrology, and then you go to initial head, and then like my initial head, I will just put any value like 111. Okay. So again, like how to define this one, you go to like edit, like go to data, edit data sets, required, hydrology, and then like initial head, and then you put like here 110. Okay. So you get something that looks like this, and then you click apply. Okay. That's why it probably didn't converge. And then like if we run it again, and then you click like save. Do you want to replace this one? Yes, I want to replace this one. Then like see now it's running. Let's look here at the list file. Now, okay, now here is what we got. Okay. So this is like one of the outputs. So here, this is the head observation, like the 12 value, like I have like 12 observation well. This is what I am observing in the field, and this is what my model is simulating, and this is like the difference between them. So like you see here, for example, like for B1, this guy is here. Okay. So like B1, for B1, what I am observing in the field, like for B1, okay, what I am observing in the field is like, let's say 108, for example, meter. Okay. This is what I'm observing in the field. This is like differently. So like this, like head observation, like for like B1, this is like what I'm observing in the field, like head simulated for B1. This is what my model is simulating. So my model is simulating 108.85. So my model is simulating 108.85 meters. Okay. The difference between like this guy, what I'm observing in the field, and what my model, like this is 0.85. Okay. Between what I'm observing in the field and what my model is simulating, that's like this difference is called the residual. So here, if you make this residual, that would be minus, like that would be like minus 0.85 like meter. Okay, that's called like the residual, that difference. So that's what we are seeing here. So here, this is what I'm observing, 108. I'm just approximating this, so rounding this to 108. This 108.5, and this is like the residual, like 8.7 or whatever. Okay. So like for your project, I'm asking you again, like if what my model is simulating is similar to what I'm observing in the field, this means that this model like is a good like representation of like the field condition, and I could use it for design purpose. If what my model is simulating is different than what I'm observing in the field, then this means that I still need to work on this model and improve my conceptualization of this model. So for your project, I'm telling you that the head observation minus the head simulated, like the absolute value of it, okay, should be less than or equal 0.3 meters. Okay, so for your project, I'm telling you that like I need like what your model is simulating and what you're observing in the fields are different to be about 30%. And that's like smaller, like so like you see here, for example, like the difference here, this is like about 87 centimeters. Here about 11 centimeters. Here about like 62 centimeters. Here is about like 7 centimeters. Okay. So you see, like for most of them, they are not. We got like some of them are okay. Like so, like you see, like this guy is okay. For example, this guy is okay. This guy is okay. This guy, like you see here, these four are okay. For example, but like these ones are not okay, and this one is okay. For example, this one is not okay, and this one is not okay. So now, in order to make like what my model is simulating, like so, for example, like let's look at B1. Like B1, that's here, like in this region. B1 is here in this region. So that would be like this region, where I have A. So, so if I want to make what my model is simulating similar to what I'm observing in the field, what do I do? Anybody suggest some ideas? That's one thing you can change, like change your area or change your hydraulic conductivity value of this area, right? So, like for example, I have like a hydraulic conductivity value here of 8. Should I make it like now this one is like larger than this one? So if I want to bring this one down, should I increase hydraulic conductivity or reduce the hydraulic? Right, because this is what I want. I want like this is 108, this is 100. So I need to bring this one down, right? I need to bring my head down. So to bring my head down, should I increase the hydraulic conductivity or reduce the hydraulic? I don't know. Let's see. I don't know. I mean, I have to write the equation to see. So okay. So I put like K is equal, like that's like you remember like Darcy. So like yeah, so like that would be like delta H over whatever. Okay. So here, like what I want to do, I want to like this one, I want to decrease this guy. So this means that I have to increase this guy. Okay. So let's do this experiment. So let's do like, so here, this is like here, for example, like this, we are like this is for K1 is equal to 8 like meter per day. Okay. Because like this is B1 here and B1 here like correspond to like, okay. So, and let's now change like K1, let's make it like K1, let's change it to like 15 meter per day. And let's see if we change this, or like, let's just double it. Okay, 16. Remember. Let's just like double the K1 value and see my head observation does not change. So like the head observation here would be like also the same, like 108. And then like my head simulated for like this new K value. Let's see, let's do this experiment and see what we will get here. Okay. Yeah. But before I do this, let me just tell you one more piece of information. Before I run this experiment. Let me to make let me just tell you one piece of information. Like this value here, like sum of a square difference. Like have you heard this term before? Like sum of the square difference, sum of the square is equal like in anything like that's so you heard this, you know what's the sum of the square difference? Sum of square difference. Well, you didn't study this. We heard about it, we didn't study it. You didn't study it in detail. So the sum of the square difference is the sum of the square difference. Basically, like I have like a observed value, okay? That's like my observed value. And that's like my simulated value. The difference between these two, that's like this observed value. Okay. Now, if I stop like I have like this like 12 points there. If I stop like if I square this residual, like so I square this guy, square this guy, square this guy, square this guy, and sum all of them, that will give me the sum of the square. That's called the sum of the square, or sum of the square residual. And like this is like we do this for validation, that's like the next thing. Like I will show you that. Because like to calculate this problem, this is an optimization problem. We're solving an optimization problem. But let me like so now. Like now let me ask you this question. If my observed value is very small to my simulated value, like this sum of the square difference means larger or smaller? Or smaller, yeah. It's smaller, yeah. Because like if this one is very close to this one, this will be very small, then I sum it like that, it's smaller, right? If like these two are identical, that would be 0, right? So let me write this number here, and then let's see when we make this change, how will this increase like the like will affect like our total sum. So here like we have a difference of, let me write this, so like the difference we got here, let me write the exact difference that we got. Minus 0.87. So here like we have minus 0.87 and like the sum of the squared residual for all these points is like what's this? 2.19. Okay, so here 2.19. That's like okay. Now let's make this change and like let's see how we can improve like if that will make any improvement. So to make this a change, like you can come here. You can just go to like you close this one. You can come to model and go to manage parameters. And then like here in your parameters, like I want to change this guy from 6 like to like from 8, I will double it to 16. So I just change this to 16. Then I click OK. Then I run my model. Do you want to replace? Yes, I want to replace. And then like I run my model here. So that is running. Let's look here what we have here. Then now, oh, now you see the difference. It was like like now my simulated value is like 108 and 33. So like here, like my simulated value here is like 108 and like 33 meters. So I was able to bring this guy down from 108.85 to 100.33. That residual, like that difference is now minus 0.35, and like the sum of the square errors that I got here is 1.3. 1.31. So you see, like I just like improved my conceptual model. So I make this like change to my conceptual model, and now the simulated value is become very close to the observed value. Still not within the limits that I want, like because the tolerance limit or like the threshold, like that I'm telling you, is like 0.3 meter, and this is like 0.35. So still not as I'm asking you to do in your project. Okay. But like you see, this is like like this is a very tedious process. Like I'm not gonna go to each of these parameters like to make these things match. I'm not gonna go to each of these parameters. Like you see here, like this is my model parameters. I'm not gonna go change this one like one by one, like to get like a close match between like what I'm observing, like what I'm simulating, right? Is this like a nice thing to do, or this is tedious? It's not tedious. So what we can do, like you can do, like this, what we will like be doing is that we can do like automatic model calibration. Basically, we will like run an optimization algorithm, and like this optimization algorithm will do this job. Okay, so like this is like so. Let me show you how this works. So here, for example, I have like one parameter. Okay, like this is like some parameter value that I have. So like for K1, for example, I will define like a distribution. Let's say like a normal distribution. It could be also like let's say like a uniform distribution. It could be like a normal distribution. It could be any distribution you want. But let's say I will like define like a normal, like a uniform distribution that could be from like A, for example, or like 6, for example. That's like the lower bound of it, and like the upper bound is like 4. And like let's say K2, like I have 21, let's say I will make this from like 10 to 40, any number. Okay, for K3, for example, I have here 300, so that could be like 200 to like 400. Okay, K4, for example, that's 41, so I will define like distribution starting from like 30, 60. K5 example, that is like I will go maybe from 500 to like 500 or whatever. Okay, K6, for example, okay, that's from 100. So that would be like my private, like for example, like this one here. I will like K1, for example, I will define like my minimum value will be like 6, and my maximum value will be like 30. And this will be like, okay. And that's like uniform. So what the optimization algorithm will do? Let me close this one. You run it again. Okay, here. This one. So basically, what the optimization algorithm will do, like given this like prior distribution that I defined, it will just take a sample. Like we'll randomly take a sample from each of these ones. It will like take a random sample that will like for your case, or like for example, from this one, it will be like taking that's just a random sample, like 7.5 within this range that I'm giving. So like this one, for example, it would be like 15.9. Then for this one, it will take a random sample 301, for example. And for this one, it will take a random sample this like for this one, it will take a random sample before the 2.0. From this one, 808. And from this one, 111. Okay. So it will just like take a random sample from this one. It will use this random sample to write your model. Like use this random sample, it will write the model, run the model, get like the simulated value, compare it with the observed value, and then calculate the sum of square difference. So it will like run this sample, and like let's say for this sample, I got like a sum of square difference, for example, of like 2.1 or whatever. Okay. Then what it learned from this like from this step, it will update the sample. So it will update like this value, and then again update this value, change like this value, and change this value, giving this step like giving this range that you define. It's not gonna go either above or below. So given this range, it will update this value, and it will create the model, run the model, get the simulated value, compare it with the observed value, and then get like SSR, and then, for example, this will be for like iteration 1, then like for iteration 2, like this number might be like 1.1. And it will keep improving until it reaches the stopping criteria. The stopping criteria is that like do like maybe 20 iterations. So like this would be like 20 iterations, like this is like 20 iterations, and let's say that would be like 0.01. Or until this number like reaches certain threshold. And I think we'll just run this with whatever like default parameters at this. But generally, this is basically how it will work. And like how it will decide like how to move from like this would be like here, like this one, and then will be another one for this one, and another one for this one. How it will decide this K value, again, this is based on the optimization algorithm. The optimization algorithm is on the solution, and then we'll see how we need to improve this K value in order to minimize like this. Did you study optimization before or not? Like not in Comp2, because I teach this in Comp2. So like in Comp2, the student, I'll give them an optimization problem, and then they will code with Excel. It's something very similar to this. Like there is like a objective function that they need to minimize, and there are like some decision variables. So these are both your decision variables. The optimization will change like this decision variable, like we change like these numbers, so that to minimize like this number. Like this is your objective function, minimize this number. Okay. That's like code optimization. You have like a decision variable, you keep it changing that in order to minimize your objective function. And here your objective function is based on this thing. Okay. But an optimization could be like your objective function, like here your objective function is based on this error. And another thing, your objective function is whatever system. I think like I don't remember what the problem I gave to my computer. Okay. But anyway, so that's like yeah, like in engineering optimization, these are like that's what engineers do a lot. They optimize. Here, what you are trying to optimize is that you are trying to minimize like the difference between what you are observing and what you are seeing on the screen. So let's take like I would say like 5 minutes or so break, and then once we come back from the break, we can do this model calibration. So let's take 10 minutes break. And during this 10-minute break, if you have any question about your model, I can answer it. So let's get back at 2:15. Okay, so we get back at 2:15 p.m. And like during this break, if you have any question about like your model, like your model is not running or something, then I can. Answer. Let me also give you this. This is what we're doing after the test.
I mean, going on. What? So that's just going on. Photo. Bro, yeah. I mean, I was Watching it be like easy. Like it ends up being just like. Ease with ease. It's actually where. Reason like we really start going into like hard getting involved, but we don't really get involved. This was just step one. Now it's time for automatic calibration. Yes. Well, it'll do it by itself.
Okay, so let's get back. Let's do this. So I think like most of you are like seems to be like doing okay in this part. He was getting like over there. He was getting an error that like the simulated value was like an undefined number, and like the reason like when you get like this simulated value as an undefined number, this could be because you have a dry cell. Like it's either you have a dry cell, and when you have a dry cell, then you will get this undefined number. And like the reason he had like a dry cell is because when he added like the recharge, he added with a negative value. So basically, instead of like adding all this water like to the aquifer, he was removing all this water from the aquifer, and it was like leaving all these cells like at this part dry. And when the cell is dry, it will just give you like with no water, it will give you like an undefined number or a big number. Like you will get like if so like if you are running, for example, and you got something like this is like an undefined number, this means that like you have a dry cell. And like if you have a dry cell, like then look for the reason, like why this cell is dry. Maybe I'm pumping so much water that I dry the aquifer. In that case, that was negative. He was pulling all the water from here to dry from here. He also had like the river was wrongly defined here. So when you do the river, like the river conductance, let me show you like another mistake he had. Like make sure that you don't have these mistakes. Like when you do the river here, let me show you like the river. So let's get back to here. Let's see all like the river. Oops. Like in this river, like in the river here, like MODFLOW feature, like the river conductance, he was doing like calculated. Like okay, we are not doing this calculated. Like we are just entering the direct conductance of the river because we calculated it. Remember, like last time for this cell, I took the actual dimension of this cell. So I'm basically giving that actual like conductance in each of these river cells. So this make sure that this is direct and not calculated. Okay. That's the two errors that I found so far. Okay, so now let's get back to doing this. So now our objective is that like we want like here we have like this parameters here. We want to change these parameters. Okay, we want to change these parameters in order to get a good match between what we are observing and what we are simulating. And again, as we've seen before, that changing these parameter one by one, it's not only tedious, it will never going to happen, because the problem is if you change the hydraulic conductivity here, it will affect the value in all the rest of your model. It's not only going to affect the head value here. So like let's say you fix this one, then you change the hydraulic conductivity here, then this one will get screwed again. So basically you cannot do this manually. You have to do it automatically. So we will see like how to get like a program that could solve an optimization problem to estimate like this value for you. Let me bring this back to 8, for example, like to what it used to be. So like I will put like this here as 8, this is 21, like whatever values that I have here. So like keep it like whatever original conceptual models that I have. So I will like do this one, and then let me now save this. And like now, you see, let me show you something. Like when I do this, like this is the model setup. When I run this model, see how it flooded my folder with all these file, like input and output file of MODFLOW that ModelMuse created and MODFLOW is creating. So now if I want to do this for model calibration, just save this as a new one. So basically come here and then do save as, okay? And then like make a new folder. If I were you, I'll just make it in a new folder. Otherwise it will be a mess. So like make a new folder, call this like model calibration. Okay. And then like you can change this project name also so that you don't have like, you don't confuse them. So I will call this instead of model setup, I'll just call it model calibration. You are group 2. Then I will click save. So then it will tell me, I don't know, whatever happened here. So like if I go here, this is the model setup. Now I have to forget about this. This is my original model, or like my original conceptual model. And here that would be my model calibration. So that would be this one. Okay, so and when you click save as, you will already have this one. So I have like here under this directory, model calibration, I have model calibration dot GPT. And GPT, this is a file extension for like a ModelMuse project. And it will have everything. So like if you want to share this file with someone, you don't need to send him you don't need to like if you want to share your model with someone, you don't need to send all these files. If you just send this file, that will contain everything. Okay, because that's basically your project. Okay, so now I have like this one, and I will start like the model calibration using PEST. So again, PEST, this is the software. It's called, I think, parameter estimation software, and this is just software that you could use it to calibrate any model, not necessarily a groundwater model. So if you have any other model, whether this model is like a transportation model, structure engineering model, you name it. If you have like any model, you can use PEST to calibrate this model. Okay. But here we're going to use it just for calibrating like this MODFLOW model. So to use PEST, and PEST again, like let me also tell you something. All these programs, they are not related, like because MODFLOW, that's one thing. PEST, that's another thing. And what ModelMuse is doing is ModelMuse is just a graphical user interface for all these different softwares, for all these different codes and models. But they are not related. Like PEST is not related to MODFLOW. PEST was developed by some guy in Canada. MODFLOW, for example, was developed by the USGS. This ModelMuse, this graphical user interface, that was developed by also some guy from like the USGS. And this is just a graphical user interface. You could input all these data that you have here. Like, for example, I never used this before. Like, I'm just using this for teaching purpose. What I used before, I would use like a programming language to enter these things. And I told you can do this with MATLAB, for example, or with Python. In Python, there is a tool called the FlowPy, which you can use, for example, to enter these things. Okay. And again, all these tools would be developed by like different people, because but MODFLOW itself is widely used. So you'll find it in integrated in MODELMuse, and you will find it integrated in so many other groundwater and surface water modeling software, because it's widely used. Okay. I mean, this is like the in industries, this like the software that they use. Okay. Not only in academic research, but also in industries. That's like the most widely used software. Code different. Again, MODFLOW is like a numerical, is a code that will solve these plot equations for you. That's all what MODFLOW is based on. The definition of K and the definition of W, MODFLOW will solve for H. That's all what MODFLOW do. Yes, you are wondering. Now, okay, let's now run PEST. So now we have this one. So to run PEST, you first need to install it. And again, to install PEST, that's something that will take like half an hour. So I'm not going to do this in the class. I already sent you the link and the video. You can check this. I'll just give you some hints. But anyway, to start doing this, you go to like model, and then you go to PEST properties. And if you go to PEST property, you will see like PEST status is inactive. You change this to active. Okay. So that's the first step. Again, let me show you how to do this. You go to model. So everything here will be under model. So you go to model, you go to like PEST properties. Under PEST property, you make this active. Now, so that's the first thing. The second thing, similar to MODFLOW, MODELMuse again does not know where PEST is. So if you click here, that's where PEST is. So here I have like PEST 17, and under PEST 17, you should have all these other things. So you should have PL-PROC, you should have groundwater suit, and I think you should have like PEST extension. So I sent you like, I'm not going to do this in the class, but I already, like if you go, I sent you an announcement, a class announcement 2 weeks ago telling you to do this. I will just show you here, laptop and software installation. So like, this is like, if you go here, basically, this will have like an instruction on how to do this. So for example, for PEST, this like you need to download this file and unzip them. And after you unzip this file, make sure that they are all under PEST 17. Not only make sure that they are all under PEST 17, for PL-PROC, let me show you. Let me show you in the photo how this will look like. So you'll download them, you will unzip them, and then after you unzip these things, so here I have them installed here. So like after you unzip these things, they will all look like this. Make sure that PL-PROC, like this one's particularly, like is like, so you see this PL-PROC here, like copy this one and make sure that it is here, that it exists here in the under direct one. So if you like, I already have it, so I will replace it. So make sure that all these executable are here under PEST 17. So this is like the one of the errors that you will get. Like if PL-PROC is not here, you will get an error. It will tell you I cannot find PL-PROC. So make sure that like PL-PROC, like this guy, copy it and put it under the main directory. That's like the first errors that you will get. The second errors that you will get is that it will tell you the file name or file path cannot contain a dot. What does this mean? It means that, like you see here, this is my file path. So you see my file path start from like C all the way to here. If there is any dot here, like for example, fall dot 2023, that's not going to work. PEST will not work if it finds the dots anywhere in the file path. Similarly, if there is a dot in your file name, let's say this mc.g2, it will not going to work. So make sure that your file path does not contain a dot. Like if there is spaces, it's okay. If it contains a space, that's okay. But if it contains a dot, replace this dot with an underscore. Okay. So if you don't have, like, this is the two most common errors that you will get. Like it will tell you that your file path has a dot inside it, replace it with an underscore, or your file name has a dot. and replace it with an underscore or remove it or space or anything. Okay. So that's all I will say about this part. If you didn't install it, I mean, just follow with whatever I'm doing. Okay. But anyway, make sure that like, so when I click here, I will have like all these things. I will have like my groundwater suit. I will have the PEST X and this one, and I will have like, so your computer should look something like this. Okay. If it looks something like this, PEST will run. If it does not look something like this, it's not gonna run. Okay. And then you just check the tutorial. Okay. So then you click OK. And now, once I did this, I can go to my model parameters. So now if I go to my model parameters, manage parameters. Okay, now I have to activate PEST. I did activate. Like, so you go to here, model calibration. It's inactive, like make it active. So I make like PEST active. So I select PEST active. Then you click OK. If I clicked OK, then go to like manage parameters. And now you see I have all these other things that were not there before. Like before I only had up till here. Now I have all these other guys here. So like you see all these other guys. Basically here, this is like your lower bound. Like, so for example, like remember like here, this is number, you have a lower bound for this distribution. So let's say this is my base, like my value, my model parameter, the lower bound for this parameter, let's say like 6, for example, and let's say for this would be 20. This value should be like smaller than 8, and like this value here, the upper bound should be larger than 8. So here, for example, I could make this like 15, for example, and I could make this 30 or whatever, okay? This guy, for example, I could make 150, and I could make this guy, for example, I don't know, 400 or whatever. This guy, I could make it like 30, and I could make it like, I'm just defining like the range that the optimization will be using, okay? This, I could maybe 500, and this guy, for example, I could select maybe like 900 or whatever, okay? This guy, I make like 100, and this is, no. I need also to define which parameter group to, so because I could have many parameters, not just the hydraulic conductivity. I could be calibrating the hydraulic conductivity, I could be calibrating anisotropy, I could be calibrating my boundary, I could be calibrating recharge. So that could be also. So basically you define a parameter group here. I will just call it like H group, for example. So H group, and then you select here like the parameter group, you select the one you define. So like the H group or whatever, you can give it like any name. Okay. So you select like the H group here. You select like the H group here. You select like the H group here. So you should have something that looks like this. Again, like you define your upper and lower bound for each parameter. So you have 6 parameters, you define like upper and lower bound, like this is like we're going to use like uniform distribution. Yes. So H group, you go to parameters group, and you just give it a name, like, okay. So like H group, this is from here, parameter group. So like you have parameters, parameter group, you give it like an H group, and then that's like what you will have. Say again.
When you make the group, you have to change anything? You're making the group?
No, no. Yeah, and like the only thing you have to change after you make the group, the only thing you have to change is that you have to assign like each parameter to group, okay? So like each parameter, you need to assign it to group. So basically, and you just assign it one by one. I mean, I don't know how you can assign all of them at the same time. Just select them one by one and do it one by one. Okay, so we have something that looks like this. If you all have something that looks like this, then you click OK. Now we have to run the model one more time with this new settings. Like that when once we activate PEST, like we have to run the model one more time. So you come here, you like run MODFLOW. So you click here, run MODFLOW. And again, you can just run MODFLOW here. So I'm running MODFLOW. If I look here, I should look here. I should be getting like the same numbers that I got from the previous one. So here, because I didn't change anything. So I got like here, like this is here for this one. I got like this one for this one. Okay. I got like the SSR 2.109. Okay, similar to what I got here. Okay. So now I am like ready to run like my automatic model calibration. We did a manual model calibration. So this is like a manual model calibration when you change them this one by one, which is like tedious. Now we will do an automatic one. So we close this one. To do an automatic one, first you have to come here. Like you see, this is how to run MODFLOW. And you see this little arrow here. Like you see this little arrow here. If you click on this little arrow, it will give you these guys here. Now you click the last one, export PEST control file. And like here, you run PEST check. That's like how you do it. You run PEST check, make sure that there is no error. If you will have an error, if you did like, again, you can, let me just run PEST check. Like you click OK. Then you see here, I didn't like no errors encountered. So when you run PEST check, you can get no errors encountered. Again, you could get like, let me show you like this document. I put it here already. See like full screen. So in this document, like these are possible errors that you could get. Like one error is that cannot find PL proc. If you cannot find PL proc, that's because the PL proc is not on. So if you got like this error PL proc cannot find PL proc, this means because PL proc it needs to be here, like under PEST 17 PL proc need to exist, not here, not under PEST 17 PL proc. So that's like one error you could get. Another error you could get is like dot exist in the file name. And dot exist in the file name, for example, like here, for example, I have a dot here. CW full, like whatever. If I have this dot, it's not going to work. Or it go like in the file path, or a dot exists in the file name. Like you see here, mc.1.gpt. If I have a dot here, it's not going to work. But for this one, it's going to work. Like I replace like this dot here with an underscore, and I replace this like dot here with an underscore or no underscore or whatever. If you have a dot here, it's not going to work. This is not going to work. Okay. So these are like the two possible errors that you could get. If you got any other error other than these two errors, this means that you did a problem in installing PEST. Like you didn't like basically this means that like for when if you got another error, this means like here you have like these four of them. Maybe you didn't do all the four of them. You like in the previous session, for example, I had one student. She only did this one like PEST and groundwater suit and PL proc, but she didn't do this one. So like when she didn't do this one was missing, then it's not gonna work. Okay, needs to be the three of them, and the three of them, like the four of them, like need to be all be under here. Okay, and if you have a problem with PEST, like I can show you, like I can help you after that. Okay, so you got a problem there? You got like, so basically, let me do this again. Like when you come here, you do this like PEST control. You do this one here. Yes, and then if you run this, if everything is okay, then it will tell you no error encountered. Okay, no error encountered. I mean, I can help you like if you have a problem now. Now before this, now you are done. So now you are done from this step. You just run PEST. So like to run PEST, you come here. It changes from PEST check to run PEST. Like you choose this, like not this one. You choose run PEST, and then you save. Replace, yes. And now PEST is running. Like my computer is slow, so that will take like some time. And while this is running, let me just say, like your computer will pass much faster, that will work. Your computer it will take because this is like very slow. Has a very like let me tell you what's happening. What's happening here is that my PEST, what PEST is doing, takes like a parameter sample, creates a multiple model, it runs a multiple model, creates a related value, paired with observed value, and calculate and sum of the square difference. Let's say. Then based on this number, it will decide on the next equation. So it will go for another equation, create another sample, and like do the same. And it will keep doing one iteration after another. I think like the maximum number of iterations that I find here is 20. So it will keep doing this for like 20 times. And then like the ending, sum of the square difference would be much smaller than this. So here, for example, this one we have like 2.1. The ending one should be like less than 1, maybe 0.5. So that's what it's doing. It's just keep generating these samples, running the model, and for each sample, it will have like it will keep adjusting these parameter value to reduce this number. This is called optimization. And you go to like where I showed you like this video, like my YouTube channel. I think for the Comp2 student, I put like the videos online. You can go check like the optimization video if you want to learn more about optimization, or not just you can just go online and check any other. There will be much better videos even about optimization. But basically, that's like how optimization works. Like an optimization, these are called like decision variables. This is called your objective function, and your objective function could be like a maximization or a minimization. Like I want to maximize those by changing my complete mix while I'm maintaining a certain like strength to my concrete like picture. Okay, so that would be a constraint. The constraint is that like the strength should not go full below this one, but like play with all the other ingredients to reduce my cost. So that like the optimization would play with the mixing ratio, would like change the mixing ratio, then it would calculate like the strength, for example, like doing this mixing ratio that you have, and then it will calculate the cost based on this mixing ratio, and then keep playing with this until like you get like the minimum, like the maximum profit or minimum profit or whatever you are doing. So like for the optimization, you can minimize, like here this is a minimization problem because we want to minimize the error, but in other cases there could be like a maximization problem. And I think, for example, like for the Comp2 students, the problems that I gave them is that I tell them like to maximize like treatment efficiency while reducing the cost, because like you have like different contaminants and each contaminant has like different costs for treatment based on like different parameters. So we keep playing with this, and then they find like the optimum ratios of chemicals used to reduce, for example, increase like the radiation of this contaminant while like reducing the cost. I mean, this is very small. I think if some of you run it successfully, you don't have to ready to do. Did any of you finish? Run it and finish? Yeah. Any of you already run it and got like a result? You got the result then? Okay.
Yeah, open up and.
Yeah, just wait. Just wait with this result. But yeah, this is like a super slow computer, like the job like mainly like why is this taking time? Because it is why is this taking time? Because it's creating all the formulas. It will create like 20 models or something. Oh, battery is lying. Let me go get like the charger.
You know what? I like the mine pyramid better. Yeah, that's what I said.
Yeah. I don't know what.
Yeah, show again when you calibrated the PEST. Okay. I can't get it. Let me just like it's like charging this one. Okay. Yeah, this one is much faster. So yeah, like if you run this, like your computer will be much faster than this one. This just computer is very slow, but let's see what we have here. Okay, I have to do this again because my computer got like disconnected, I think. So let me run this again. And while this is running again, I will be walking around like to help you. So basically to run PEST, like you have to go from run chat to run PEST, then you click save, and then you click yes. And then, yeah, like my computer, this computer is very slow. So it will like do this. But let me move around here. I think we're done already. We're done already. I think all of you are like you're the table you're on. This is not No, just wait. So here we I mean, the computer is like very full computer. Okay, so finally it is like the computer did something. Finally, computer did okay, so let's look at this together, please. Okay, let's look here together for this one. So now we run PEST. Once we run PEST, like it will normal, like it will tell you that your let me tell you what it tells you. Anyway, there's this thing showing. Okay, so like let's go back to our file. So yeah, well, once you run PEST, this is important. Like once you run PEST, before you do anything, and even before you look at the result, remember PEST and like this graphical user interface are not connected. So basically, to make sure that like this model here update, like you have like your new model, like your new calibrated model, you need to import this model. So basically, like you come here, you go to File, and then you go to Import, and then you go to Model, like tells you, do you want to save? No, I don't want to save. And then like here for the grid origin, I will just put this one. I will change here like the grid origin. Remember, like when I set the program at the beginning, I told you I will just make the origin 0 and 0. Then when I need to change it, I will change it. This is where I need to change. Just put the reasons that I'm changing the grid origin. Yeah, this is from here. Like, let me show you again, like how to get this one. So like you come here. Oops. Oh, my model disappeared. I don't know, this computer is acting weird. And my model disappeared. Let me open it again because the full screen. I don't know why my model disappeared. So my model terminated. But anyway, let me open it again. Model use. Okay. Apps anywhere. With apps anywhere. Model use. Open the model muse. I hope this is even still recording.
Oh.
Okay. So you come here, like I open an existing model views project, so I can click next. And let me, I mean, this one didn't, yeah, I mean, let me do this. Oh, but this one, okay. So like you come here and then you do like import and this one, you click no. Then I put like this origin here and then like file name. I click like this file names that I want to import and then I click OK. And then now I have my model imported. Okay, so now like please all like do this step, please. Before you do anything, just go to this step, go to import, here, MODFLOW here, click no. Like you can set like the grid origin, like whatever here. And then like you can select like the file name, like you can select like this file name here. And then like click OK. And then you will have like this model as imported. Now, if you go to your parameters, like go to like manage parameters. Now, like you see here, my model has like very different parameters than what it used to be. So now this is like my new parameter values that I have. Very like different because now this is my new model. I can run my model. So you see here, I can run my model here. Save as, like I can run my model. So if I run my model and my model is running fine, I could check like now the improvements that happen, if any improvement happened. So now you see here, it's like now, like you see here, this value, for example, here I have 2 centimeter error, 6 centimeter, like they're all very small error. Like the largest errors that I have is like 16 centimeter. That's here, I have 11 centimeters, that's here, but all of them are very small. My SSR, like you see my SSR value, it dropped from like 1.3 to 0.07. So that is like, now I can also, so this is like another way to see this, like like this one thing. Another thing you can look at is like the PEST file, like, so like the PEST record file. So like if you go here, for example, to fall, no, not to fall, like you have something else. Okay, like if you go here, project like section 2, like model calibration. If I go here to model calibration, you will find this file like the PEST, like this is important, like this important, like the PEST file is called like whatever your model name dot rec, REC. Okay, so search for this file. The file was an extension of REC. Okay, so it should be somewhere here. Okay, so here, and then click, you can open it with Notepad or whatever text editor you have on your computer. And like this will tell you the summary of the PEST run, like how many iterations it did, what is the solution after each iteration. So we are only interested in the solution in the last iteration. So here, this is the solution of the last iteration. So the last iteration, this is what I observed in the field. This is what my model calculated, and this is the difference. Almost the same number. Like, and this is for all of them. This is my prior information. This is what I started with, and this is my calculated value for these parameters. Okay, so this is my prior value. This is the new value, new hydraulic conductivity value. And if you want to see the sum of the squared residual, you will find it here. So like that would be like the contribution of 5 from, that would be this one. That would be like, this is just the numbers that I wrote here. So this number should be similar to what you get when you run MODFLOW. So basically, this is the sum of the squared residual. Like, remember, that's your objective function. So that's like your objective function value, which is your sum of the squared residual, or sum of the squared, sum of the squared difference. So it should be this number. Okay. So basically, that tells you how good your and then for your report, you will write these numbers. You will write like for my conceptual model, for example, I got this sum of the squared residual, but for my calibrated model, I got something else. Okay, so now now I have like now this model is running fine. And like now I don't need really to make any change to it. Now it's a calibrated model and I updated it. Now I want to plot my value. I want to see like to plot this value. I can plot my hydraulic conductivity, my new hydraulic conductivity. For example, I could come here. I could come to like data set, for example, not like a data set required hydrology, KX, then apply. Then that would be like my new hydraulic conductivity values. So here, for example, that is 15, that is like 30, this is 190, for example, this is 900, and this is 200, this is like 60, okay, whatever like these values are. So, I mean, for you, it will be different because like each conceptual model is different and the calibration will be different. So you will not get the same value, but like, again, like as long as what we care about is that we care like the head observed and head simulated should be this one. So that's like if your head observed and the head simulated for all of the observation point is less than 0.3 meter, less than 30 centimeters, then you're fine. If not, you can change this like prior range, or you can change your hydraulic conductivity field. Like you could change these zones until it calibrates. But in that case, I think we met this like 0.3 meter threshold or criterion. We can also plot our head. So to plot our head, you have to import it. So basically you come to file, import, this is our model results. So that's like the model results. And like that would be this one here. Like the 1.hfd. Like the head HFD, like whatever your model name is. That would be the head. So you can click like open here. And that's like head, you only have one period because this is like a transient, like a steady state model. Now it tells you how you would like to plot the head. Would you like to have like a grid or like a contour or a grid? I will just usually we use contour for the head. So or you can, I mean that really we can also use the gridded data, but I want to have a contour to compose it over this one. So if I click OK, then this is the model solutions. This is here, this is the H that this model is simulating. We are doing all this to get this H, which looks something like this. And from here, you can see like the groundwater flow direction. So for example, water will flow in this direction, like this, like this, like this, to here, to here, to here, to the river. So that's basically your H that you are solving for. And that should be similar to what we observe it in the field. Okay, so that should be like similar to what we observe it in the field, because we know that like the difference between these two is very small. Like the largest difference we have is like 11 centimeter or something. You can have this picture for your report, so you can do this. You can come here like export image, so you can like come here export image. You don't need this one, like you can hide this one. So you can like this contour legend, for example, because you already have the value here, and you get something, a figure that looks like this. So for this figure, you can copy it or you can save it. I will just copy it for now. So you can make like copy image here. If you click here, copy image, and then I will just like open file like this one, for example. And then I will like come here and paste it. Okay, so now I have here, this is like my hydraulic conductivity field and my head value, for example. And you can show like for your report, you can show a figure like this for like your conceptual model, like or like your manual calibration, whatever. Like if you did this calibration manually, and you can show another one for like your calibrated model, like your model that's calibrated. Okay, so now we have a calibrated model. And we are ready now to use this model for our application, because now this model represents like the field condition. So now we are ready to use this model like for our field application. But before we do this, before we use the model for like the field application, we need to present our calibration result. Because if somebody, if like someone is like reading like your report, like when you do like a model and you create a modeling report, the most important thing that like the reviewer will look for is this a calibrated model and how well this model is calibrated. So that would be like the most important thing, because if this model does not represent what you observe it in the field, and like you are estimating something and you are observing in the field something else, this means that this is not a representative model. So you need to show how or like you need to show basically the calibration results. So like to do this, to do this, I think you can come here, okay, like to visualization. Okay, I think you have to import this results first. Like to do this, you have to import this results first, and like to import this results, I think you have this. Yeah, you have to. I think you like let's see if this results will be automatically here or we need to import it. So like optional, like yeah, that's the optional model results. So here we only have like this. We need to import like PEST results. So to import PEST results, I think you can come here, import, and you can select PEST, like how to import PEST results. Let's see. You have it here. You need to activate PEST, the data visualization. The status active. This observation. Yeah, okay. So like to do this, like you from data visualization here. Okay. Yeah, here. Like you see this how you import it from. Like you go to head observation results. So that's you import it from here. Not head observation. Like there should be okay. It's not like you don't see it because you need to activate PEST again. So like you come here, you go to PEST again. It's inactive. You need to activate it again because this is you imported a new model. So you need to activate this one again. So again, like you come here, you go to model, PEST properties, you go here, you activate this one again, then you click OK. And then once you activate this one again, if you go to data, then you will see PEST now started to appear here. Okay, so now you could import like the PEST results. That would be this .arc, this one, is this file. And then like you click apply. And if you click apply, that will import like the results of the PEST. So here, this is basically the best results that you have, okay? So this is like for example, the measured heads, this is the imported heads, this is the residual. This is like your parameter, for example. This is the ones that you started with, this is the modeled one, and this is the residual. So you can find something that looks like this here. Now we can make some graphs, for example, like let's do, for example, like, so this is just to visualize the values here. Now let's do the graphs. So for this graph, I don't want to visualize, I just want to visualize the information. So I will click this one. So here, let me show you, before I show you this graph, let me show you this graph. That's a much easier graph to see. So this graph, like this one of the graphs that you need to show in your report, and this is a very important graph. All of them are important, but like each one serve a different purpose. So basically what this graph is telling you like here, I observed this value and this is the corresponding simulated value. Like here, for example, I observe it like this is what I observed, this is what I simulated. So if all your dots fall in this one-to-one line, this means that this is a very well calibrated model. If this model was not very well calibrated, your simulated value, like this is, you observe it here, your simulated value will be here, for example, or here, or here. But because all these dots fall on this one-to-one line, this means that your simulated value and your observed value are very similar. So like a reviewer, the first thing the reviewer will look at is like this, like simulated versus observed as a one-to-one plot. If he sees something like this, then he will know, okay, you are doing a good job, because like what you are observing and what you are simulating are like very similar. So that's like one figure you can plot. Another figure you can plot is like the residual versus the observed. So basically, this is like here at this point when I observe it, this one, this is the residual. This is the difference between the observed and the simulated. Like the highest residual, remember, I have is here, like at this point. all my residual fall between like 20 centimeter. I don't have anything larger than 20 centimeter plus or minus. So this means that like all my error is less than 20 centimeter. Remember, I told you your error should be less than 30 centimeter, 0.3 meter. Here, all my error are less than 0.3 meter. But more importantly, what I get from this figure, the most important things that I get from this figure is that my error are randomly distribution. Like, for example, if all my error, for example, was here, like I have all my model is systematically overestimating the head or systematically underestimating the head, then you will find all these error will be here or all these error will be here. So that is the second thing that the reviewer will look at, is that are these error random error or you have a systematic problem in your model, like your model is systematically overestimating or underestimating head. So that is the second thing that like the reviewer will look at. And that one will be the same as this one, because here we are not doing weighting. So basically, these are the two figures that I want you to show in your report. Like this one basically shows like your simulated versus observed. If you did a good calibration job, they will all fall on this line. And here, for this one, I will see that I will see that how your error like is randomly distributed. Your model does not have a systematic error. You can also visualize this error on your on here. So like, let me show you how to do this. So if you come here and you go to like gridded data and like, or not gridded data, like I think it could be gridded data. Let's check. And then you come here, like under optional, I think model results of this one. So, okay, like user defined, I think it would be under user defined and recharge up here. Let me show you like, let me see how to, let me just show you like how to visualize these ones. Apply PEST observation results. Okay. So under grid, none, apply, and then PEST observation results, select show weighted residual. Ah, okay. So that's not from here. That's from here. Like PEST observation results. Like here, you come here first. Let's answer. Let's undo this plotting that I have here. Here is the slope. Okay, let's just come here. Let's not plot anything. Like click apply. So now I don't have anything plotted. And you see here now I plotted this one. Like how did I plotted this one? You come here from plot, from PEST observation results. And I think if you just clicked here, they will also plot them here for you. Like don't want to plot the prior information. You want to plot the prior information. You just want to plot like these ones. So basically, it will plot them for you. So here, that would be like here, for example, a small like error. Let's see the legend of this one. We see like here, import, like export, image, and like you see like remove this contour, contour legend. Okay, so basically that will tell you like the positive number. Let me, how many minutes we have? We still have 3 minutes. Okay, let me copy this image. And let me just paste it here. So this is a visualization of your error. Like you want to see like the visualization of your error. So basically here, this is a positive error, like the maximum positive error you got is like 16 centimeter, which would be like this guy here. And like the maximum negative error you got is like 8 centimeter, which would be this guy here. And like you see your model is like these error are random. Like, so here, this is positive, negative, positive, positive, negative, negative, positive. So you don't have like a systematic overestimation. So you could also like, this is just like, this is your residual, your error. So this is telling you the magnitude of your error. So like the largest positive error I have would be like here, and that would be about like 8 centimeter. And the largest negative, I mean, like the largest negative error in here would be like negative 8 centimeter. And like the largest positive error would be here, and that's like 16 centimeters. So that's like another figure you can present to the reviewer to show him how good is your model is. Okay, and how your model was able to simulate like the field condition. I think that's all. Like, so now if you did up till this step, you are about 80 or 90% done with your project. I mean, other than the report, of course. But like you are 80 or 90%. Like next class, what we will do next class, now we have a calibrated model. Like now this is a model that we can use. Now we have like whatever aquifer we have in nature, we have it now on our computer, and we can try everything we want. Like we can start pumping and see how will this effect go down for our paper and just like 12 observation. We can put them in industrial area, and then we see how will this impact our recharge, and then how will this make us need to reduce our pumping in order to not so much go down. Okay, so that's all for this class. And like next class, like come up with this model, make it ready, and then you will finish your project. Okay.